Hello, chemistry gurus. Today, we're going to talk about famous models in chemistry, but not the models you see here on my screen. We're going to talk about molecular models. Our learning goals for today is to classify the molecular geometry for molecules using the VSEPR theory, to explain the role that non-bonding electron pairs play in molecular geometry, and finally to predict the bond angles in these covalent molecules. Now, before we get into the lesson, I'd like for us to take a few minutes to explore the PhET simulator that you and your table partner will be using a little bit later as you pair up on your Chromebooks and get into Google Classroom. Alright, so on the PhET simulator, the purple atom is your central atom, and you always classify your VSEPR shape based on what is around the central atom. Now, if there's no central atom, I'll go ahead and go to that. If there's just two atoms, it's always called linear because this is a straight line. But once you add multiple atoms to the central atom, you start classifying it based on what is around the central atom. Now, when atoms are sharing electron pairs between one another, they're covalent bonds, sharing their electrons, and so every dashed line, every bond here is two electrons. That's why we call them electron pairs. These are called bonding electrons. So here there's two electron domains around the central atom. Notice the bond angle is 180 degrees. Now, as you add more atoms to the central atom, notice they space out. So the angles here are evenly spaced 120 degrees apart, not 90 and 180 like you would see on your paper. You always want to classify your shape based on the three-dimensional space available because our models are 3D models. They're not flat like your sheet of paper. If you add another set of another atom here, another pair of electrons, you get even smaller bond angle here, 109.5. Now, if I take a couple of those off and replace them with lone pairs, now when you have a lone pair of electrons, these electrons belong only to the central atom. There's no other atoms sharing over here with them. So the lone pairs are kind of like going crazy over here, taking up all this space because there's nothing to hold it in. So the lone pairs always take up more space than the bonding electrons, and that's something to keep in mind as you classify your VSEPR shape. So let's get right back to our lesson and let's talk about what exactly this VSEPR theory is. The VSEPR model helps us understand the geometry of a molecule, and VSEPR is an acronym. It stands for Valence Shell Electron Pair Repulsion Theory. And just like the name sounds, it's based on the assumption that the electron pairs repel one another or push one another away. They try to get as far apart as possible. So always keep in mind your electron pairs try to get just as far apart as possible in the space available around the central atom. So the geometry or the shape of your molecule will always depend on the number of electron pairs or the electron domains around the central atom. Remember that the non-bonding electrons, also known as the lone pair electrons, take up more space than the bonding or the shared electrons. Now, before you can classify your VSEPR shape, you do have to draw your Lewis structure first. And that's what our lesson yesterday was on, and your homework last night, you had some molecules to draw their Lewis structures. And we've already gone over those answers, and so once we're finished with today's lesson, you're going to go back with your table partner, you're going to grab your Chromebook and your molecular or modeling kits. You're going to use the PhET simulator as well as the 3D models to build these molecules and look at and examine the VSEPR shapes and remember the bond angles that go along with them. So our first VSEPR shape we want to look at has two atoms on the central atom and no lone pairs. Look at here, your central atom here is the black sphere. It has two red spheres attached and there's no lone pairs on the central atom. So we call this linear, and the bond angle is of course 180 degrees around that central atom. An example of a molecule that would exhibit linear shape is carbon dioxide. Notice the carbon has two oxygens attached to it, but there's no lone pairs on the carbon. You always look at what's on the carbon, not what's on the atoms attached to the carbon. What's on the central atom is what you look at. We would call that linear, and the bond angle is 180. Now, the next structure is what I call a cousin to linear because it has two atoms on the central atom. But the difference is now we've got some lone pairs there. So in your actual Lewis structure, you would have a set of electrons here and here. Keep in mind the lone pairs take up extra space. So as you see in the modeling kit here, you have this bent or angular shape. And that's exactly what we call it, bent or angular. Some textbooks even call it V-shaped. The bond angle here is 105 degrees. Water is a bent molecule. So if you look at your Lewis structure for water here, the oxygen is your central atom. There's two atoms attached, but here you got your lone pairs here and here. So this is like a top view of the molecule. Like here's the lone pairs. So the lone pairs are actually, you have to visualize from the top view that it's pushing those hydrogens downward in that bent shape. The third shape is going to have three atoms on the central atom and no lone pairs. And when you think of geometry in 3, normally triangles should come to mind. So we call this trigonal, triangular, or trigonal's the word, planar. And anytime something's planar, that means it's flat. This is a flat molecule, trigonal planar. An example of trigonal planar is boron trihydride here. Notice the boron does not have any lone pairs on it. So actually when you draw this, you don't have to draw it this way, but when you draw it, you want to visualize that you're going to have equal space hydrogens around that central atom, and the bond angle there is 120. The next VSEPR shape is cousin to trigonal planar. It's called trigonal pyramidal. 3 atoms, but now you have a lone pair. So in your Lewis structure, you would have a lone pair of electrons, and those lone pairs again take up all this space, pushing those hydrogens down or those atoms down. So we still call it trigonal because we have the triangle shape, but now it's a little pyramid. So trigonal pyramidal. So you'll notice the pyramid sort of shape here that you get. And from the 3D model, you see also it's not a flat molecule, it's pyramidal. Trigonal pyramidal. And ammonia, or NH3, is an example of a trigonal pyramidal molecule. There's your lone pairs, going to push those hydrogens down. Finally, the fifth and final VSEPR shape is called tetrahedral. It has 4 atoms on the central atom and no lone pairs. We call it tetrahedral. Remember, tetra means 4. And the bond angle on tetrahedral is 109.5 degrees. Notice they're evenly spaced and a little tetrahedron. They're not 90-degree angles like a lot of students will think, because it looks 90 degrees on your paper. Instead, they're 109.5. Remember, these molecules are 3-dimensional. So the next thing we're going to do, I want you to get your Chromebook and get out your homework, and also grab a pack of your molecular models, and you're going to, with your table partner, build the models, the 3-dimensional models, as well as in the PhET simulator, and let me see and check you off as you get finished.